will not export these factor scores. Now I'm going to perform a basic cluster analysis on the data instead of the variables. So here we have our data. 33, row index 33, which was 35 on here, which was New York. So New York has been clustered by itself here in single linkage. Probably because, as we said before, its square distance was extremely far out. We can see here that the dissimilarity we could probably use Ward's method again. The largest distance, it's probably between here and here, or here and here. They'll probably here. This merge and this merge would probably be 3 clusters. So we can say we want 3 clusters. Use Ward's method. Scatter plot the data again. So here we have our 3 clusters of data. Probably we have our outliers again, probably in this dark blue. And we have the normal data in these other 2 colors, the light gray and then the light green. And so these are cool to look at. Plot the factor scores with the clusters. We're going to use 3 factors. And so here we have our outliers again, and our 2 distinct clusters. Sort of a mixture between these 2 factor scores for F2 and F3. Again, a mixture between F1 and F3. However, factors 1 and factors 2 seem to have a distinct line between these 2 main clusters and the outliers, whereas as we increase between 1 and 3, they seem to all merge together. So we can sort of see that F3 is a mixture of these 3 clusters. As we know already, F3 is probably a mixture between total cases, the death rate, and the population density. So that's a full factor analysis with cluster analysis. And so I'll stop here. There's one last thing I wanted to point out. We stated earlier that New York is a major outlier. I just wanted to see the actual z-scores, so we can get the row of line 33. So this is the actual data row, as we can see here. And so if we get the row of the z-score of our data set, we can see that the total number of cases is almost 3. So it's a possible outlier, actually. It would be considered an outlier, or extremely large value, and this is an extremely whopping value of a z-score for the total number of deaths. So we can basically say that this is an extreme. This is something that is totally unusual. So the total number of deaths in New York is just, it's unfathomable. It is completely out in the wild at this point. And we can definitely see why its square distance was so high, probably because of this main fact. One thing I forgot to do while going over the COVID-19 data set was actually examine the total number of cases and the total number of deaths and the death rate. So if we have our data set right here, we can actually sum up each column of the data with this function. So we can see here that we have a total of about 4,323,000 total cases, almost 150,000 deaths. And then right here, this is just the sum of the death rate, so this is just going to be complete nonsense. The total population of the US, which is almost about 330 million, and then the total population density summed up, which is going to be complete nonsense because these variables don't make sense while added up. We can actually compute the variances as well. So we can see here that there's a large variance between the total number of cases, and there's a small variance for the total number of death rate, which is going to make sense because the death rate is such a small accountable number. And so what we can actually do is we can store the sum inside a variable. And if we wanted to get the total death rate across the US, what we can do here is take the deaths and divide it by the number of cases. And so the average death rate times it by 100, so the death rate's about 3.4%. And so as we stated before, for places like New Jersey, New York, who have death rates at 7%, 9%, it's extremely interesting because most of these states with the high death rates seem to appear on the eastern seaboard, you know. So places like Michigan, up north, Massachusetts, on the east, Connecticut, and then we have Pennsylvania. So there is a little bit of a mixture, but as you can see here, New Jersey and New York, these places have the highest death rates, highest death counts. And so if we get the mean and make this into a nice little row instead of a column, the average amount of deaths is about 3,000. So if we were actually to get rid of New York and let's say New Jersey from our data set, so it's a 933. So we just deleted New York. If we were to delete New Jersey, which I think would be 30, just to make sure, let's get that row. Yes, that would be it. So if we were to delete row, so now we store that back into our variable. It's now a 48 by 5 matrix. And if we were to get the sum, it is extremely interesting to note that these two states, New Jersey and New York, single-handedly was responsible for 33% of the total amount of deaths. So we have 100,000 deaths that dropped from 150,000 to 100,000. Total number of cases dropped from 4,300,000 to 3,700,000. So we dropped 600,000 cases and 50,000 deaths because of two states. And I think that's extremely important to note out. So it's just a pretty interesting fact. So we can actually get the variances now. Actually, it's the... So here we actually have, if we were to import back into, let's say, call this original. So here we have the original data set. So we actually compared the correlation coefficients again, this time without New Jersey and New York. We can see a big difference. So we can see that actually total number of cases is more correlated with total number of deaths. Total number of cases is negatively correlated, basically no correlation with total number of death rate. So, which is exactly what it was to begin with. Total number of cases and population has increased, and total number of cases and population density actually decreased. And any other increases we can see here is that population has a direct correlation with total number of deaths, so that increased by a lot. And what else seems to be an increase? That seems to be about it. So it'd be interesting now to perform another factor analysis on this new data set without these outliers. So we can actually just do a quick check for outlier, and we can examine any other outliers that had appeared that I skipped over. So once again, so we have these three outliers. We have New York, and we have index 8, which would be 10. So Florida. Florida is another outlier, and we can say get row COVID of line, what was it? Line 10, line 8. Yes, line 8. So we get the z-score of this row. So we can see actually the total number of cases is well beyond an extreme. Total number of deaths seems to be about normal. Death rate about normal. Population a little on the high end, but not anywhere extreme. Population density pretty normal. So it's an extreme positively. So the total number of cases is definitely an extreme. The next one is 4. So if we were to do this again, 4, which would be 6. So California, we can definitely see why, has a higher z-score in terms of total cases, a higher z-score in terms of total deaths, a higher z-score in terms of population, but a less z-score in terms of population density. So we can definitely see why California is an outlier for sure. So I just wanted to add some more information back onto our previous analyses. Hopefully this might have cleared anything else up. Should be all.